this video, I will discuss the concepts of heat and phase changes. These ideas should be a review from your previous chemistry course. Heat is used inconsistently and usually is confused with temperature. Heat and temperature are not the same thing. There's a very clear distinction between the two. You may commonly speak of the flow of heat. Heat flows from the sun to the earth and from a stove burner to a pot. Heat flows spontaneously from one object to another because of a temperature difference. In the 18th century, heat flow was believed to be due to a fluid substance called caloric. So this fluid, caloric, would actually flow from the hotter object to the colder object. But through experimentation, the caloric fluid was never actually able to be detected. Heat is not a fluid substance. In the early 1800s, an English brewer, James Prescott Joule, pursued the idea of heat further. He believed that heat was related to energy or work. His experiment, which proved his theory, is shown. The falling weight causes the paddle wheel to turn, and the friction between the water and the paddle wheel causes the temperature of the water to rise slightly. Joule determined that a given amount of work caused by the falling weight resulted in or was equivalent to a particular amount of heat input. The mechanical equivalent of heat describes the relationship between heat and work that was discovered by Joule. Quantitatively, 4.186 joules of work was found to be equivalent to 1 calorie of heat. 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. It is also shown that 4,186 joules is equal to 1 kilocalorie. 1 kilocalorie is the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. As a result of Joule's and other experiments, scientists now interpret heat not as a substance and not as energy, but a transfer of energy from one object to another because of a difference in temperature. The SI unit for heat is a joule, although calories and kilocalories are still sometimes used. Joule's result was crucial because it extended the work-energy principle to include processes involving heat. It also led to the establishment of the law of conservation of energy, which we shall see shortly. Temperature, heat, and internal energy are often used interchangeably, but as we've seen, temperature and heat are very different concepts. There is also a very clear distinction between heat and internal energy as well. Internal energy is defined as the sum total of all energy of all the molecules in an object, including chemical, electrical potential energy associated with the chemical bonds between atoms and molecules, nuclear energy, and thermal energy. We will ignore the chemical and nuclear energy and concentrate solely on the thermal energy, which is defined as the part of internal energy that results in temperature. It is a measure of the average kinetic energy of all the particles. Internal energy, U, is calculated by taking the average kinetic energy of all the molecules and multiplying it by capital N, the number of molecules. But recall that kinetic energy is equal to 1/2 mv squared, or is also equal to 3/2 kT. Plugging in 3/2 kT for Ke, we get U is equal to 3/2 capital N kT, or delta U, change in internal energy, is 3/2 capital N K delta T. These two are very useful formulas, but also because capital NK is equal to lowercase n r, where lowercase n is number of moles, we can replace capital NK with lowercase nr, and we have a new set of useful equations, where u is equal to halves lowercase n RT, or delta U is equal to 3 halves nR delta T. Thus, the internal energy of an ideal gas depends only on the temperature and number of molecules, or temperature and number of moles. The second set of equations are more often used, but the first two are important as well. In summary, temperature is defined as a measure of the average energy of all the molecules. Heat is the transfer of energy from one object to another, and internal energy is the sum total energy of all the molecules, which is the average kinetic energy multiplied by the total number of molecules. If heat flows into an object, the temperature rises. But how much does the temperature rise? That depends. Obviously, the more heat you add to an object, the more the temperature will change. But what about the size of the object you're heating up? If a small amount of heat flows into a cup of water versus a large body of water, the cup of water will change temperature more because it has less mass. Also, what if we compare the cup of water to a small piece of iron? Because the materials are different, change temperature at different rates. This quantity, called specific heat, is a characteristic of the type of material. The higher the value of the specific heat, the harder it is for the object to change its temperature. These values for specific heat can be found on page 387 of your textbook. So the change in temperature of an object is proportional to the amount of heat added and inversely proportional to the mass and the specific heat. So the more heat, the more the change in temperature. The more mass, the smaller the temperature change. And the greater the specific heat, the smaller the temperature change. Or, the amount of heat required to change the temperature, Q, is dependent upon the mass, specific heat, and the change in temperature. So Q is equal to mc delta T. You may be wondering what units specific heat is measured in. If we rearrange the equation Q equals mc delta T to solve for C, the specific heat, we get C equals Q over m delta T. Q is in joules, m mass is in kilograms, and delta T is in degrees Celsius. So the units for specific heat are joules per kilogram degrees Celsius, or you can use calories per gram degrees Celsius. These are used a little less frequently than the first. Values using both units are shown on page 387 again. Let's take a look at our first problem. Through how many degrees Celsius does the temperature of water going over a waterfall of a height of 20 meters rise? Assume that all the mechanical energy is converted into heat. Pause the video for time to work on the solution. So in this problem, we're defining the mechanical equivalent of heat. We are saying that the initial mechanical energy is equal to the final amount of heat. This is basically a statement of law of conservation of energy. Recall from our energy unit that mechanical energy is equal to the sum of kinetic and potential energies. But we're going to assume that the water is not moving at the top of the waterfall, so the water only possesses potential energy, which can be calculated using the formula mgh. Setting mgh, Q, which is mc delta T, we can then plug in our values. And you'll see when we plug in values that we're not actually given a mass. But not to worry, because mass is found in both sides of the equation, and thus cancels out. so we only need G, H, and C, which we do have. So plugging in our given values, getting rid of the mass, and solving for delta T, we get 0.05 degrees Celsius. Not a huge change in temperature, but again, this just defines the mechanical equivalent of heat. The mechanical energy is converted to heat and results in a change in temperature. Let's try another problem. A lead bullet is moving with a speed of 200 meters per second and pierces the ground. What is the temperature change if 50% of the kinetic energy is converted into heat? Let's assume the specific heat of lead is 130 joules per kilogram degrees Celsius. Pause the video for time to work on the solution. So the bullet begins with kinetic energy, which can be calculated using 1/2 mv squared. The kinetic energy is converted to heat, Q, which is mc delta T. So normally, we could set the kinetic energy equal to Q if all the kinetic energy is converted to heat. However, in this problem, we're told that only 50% of the kinetic energy is converted to heat. So we have to take the kinetic energy and multiply it by 0.5, which is 50%. So we'll set the equations for kinetic energy and Q equal to each other and multiply the KE by 0.5. Plugging in each equation, KE and Q, we get the following. Again, we encounter a problem where we are not given the mass. But because it's present on both sides of our equation, it cancels, and we can plug in all other values. Solving for delta T, we get 77 degrees Celsius. Our next problem, how much heat input is needed to raise the temperature of an empty 30 kilogram vat made of iron from 15 degrees Celsius to 100 degrees Celsius, and what if the vat is filled with 30 kilograms of water? Pause the video for time to work on the solution. First, we want to find the amount of heat required to change the temperature of the vat. We know that heat is equal to mc delta T. Plugging in the mass, the specific heat of the iron, and the change in temperature, final minus initial, we find the heat required to be 1,147,500 joules. B says we're now considering the vat filled with 30 kilograms of water. So now when we add heat, it will change the temperature of the vat and the water. So we'll find the amount of heat required to change just the water, 15 degrees Celsius to 100 degrees Celsius, and add it to the heat required to change the temperature of the vat. So plugging in the mass of the water, specific heat of the water, and the change in temperature, final minus initial, we find the heat required to be 10,674,300 joules. It requires much more heat to change the temperature of the water by the same amount because it has a much higher specific heat than the vat. But because we're asked for the total heat required to change the temperature of the water and the vat in part B, we have to add the two heat values together, and we get 11,800,000. Specific heats for gases are more complicated than for solids and liquids. When gases change temperature, both pressure and volume can change. The specific heat of a gas depends on how the process is carried out. Most commonly, we deal with the specific heats of gases when kept at a constant pressure, Cp, or a constant volume, Cv. Some values are given on page 388 of your textbook. The equation we use to calculate heat is unchanged, but the specific heat value that we plug into the equation depends on the type of process. So Q equals mc delta T, but C, the specific heat, either the specific heat at a constant volume, CV value, or the CP value, which is specific heat at a constant pressure. You may notice on 388 of your textbook that CP is always greater than CV. It can be derived that CP is equal to 5/2 R, where R is the universal gas constant, and CV is equal to 3/2 R, where R again is the universal gas constant. And this is for ideal monatomic gases. You do not have to memorize these two equations, but they're sometimes useful in problem solving. These equations would be given to you in a problem if it's necessary to use them. In discussing heat and thermodynamics, we shall often refer to a particular system. A system is a set of objects that we wish to consider. Everything else is known as the environment or the surroundings. We will often study isolated systems, in which no energy enters or leaves the system. For example, consider a container filled with water at room temperature. A hot cube of iron is placed into the isolated container. What happens? Because there's a difference in temperature, heat will leave the iron. But because this is an isolated container, the heat cannot be lost to the environment side of the container, so all of it is transferred to the water. So heat flows from iron to the water, obeying the law of conservation of energy. In other words, the energy out of one part of the system, the iron, is equal to the energy into another part of the system, the water. Or, this can be stated as heat lost is equal to heat gained. So Q lost is equal to Q gained. And we know that Q is MC delta T. So MC delta T lost is equal to MC delta T gained. But how do we deal with the lost versus gained? Well, we can negate one side of the equation. By convention, we negate the side where heat is lost, but it doesn't really matter. In all examples and problems of the sort, be sure to include all objects that gain or lose heat. If we have multiple objects losing heat, then we must incorporate another MC delta T on the lost side of the equation, which again would be considered negative by convention. And if we have multiple objects gaining heat, we must incorporate another MC delta T on the gained side. Let's take a look at a calorimetry problem. An aluminum can with a mass of 0.5 kilograms contains 0.13 kilograms of water at a temperature of 20 degrees Celsius. A 0.2 kilogram block of iron at 75 degrees Celsius is dropped into the can. Find the final temperature of all three objects, assuming no heat loss to the surroundings. Pause the video for time to work on the solution. It's important to note that we're finding the final temperature of three objects, not just two. To begin, we set heat gained equal to heat lost, and we use MC delta T for each object. The water is heat, the aluminum is gaining heat, and the iron is losing heat. We also negate the lost side, and plugging in values, and performing some simple algebra, we find the final temperature to be 24.6 degrees Celsius. As we mentioned before, when heat is added to an object, it's temperature. However, this is not the case when an object is undergoing a change of phase. For example, let us trace what happens when a 1 kilogram block of ice at negative 40 degrees Celsius is heated at a slow, steady rate. until all the ice is changed to water and then changed to steam above 100 degrees Celsius. So we'll begin with the ice at negative 40 degrees Celsius. As shown on the graph, the temperature of the ice rises as so heat is being added. However, once 0 degrees Celsius has been reached, which is the melting point, the temperature stops increasing, even though heat is still being added. This is because the heat or the energy goes into changing the phase and not the temperature of the material. Thus, the ice gradually changes to water in the liquid state with no change in temperature. Once fully melted, continued addition of heat causes the water's temperature to increase. Once 100 degrees Celsius has been reached, the boiling point, the temperature stops increasing even though heat is still being added. This is because the heat or energy goes into changing the phase, not the temperature. Thus, the liquid water gradually changes to steam or begins to boil. Once all the liquid has changed to steam, the temperature begins to rise again with the further addition of heat. It's important to note that if we were going the opposite direction, from steam to water to ice, heat must be lost, and the Q's would all be negative. To determine how much heat is added, we can break the graph into segments. We will begin concentrating on those sections of the graph where temperature is changing. For the first segment of the graph, we use Q equals mc delta T to find the amount of heat added for a given change in temperature. At times, though, you will only use a small part of the segment, so be sure to choose the correct initial and final temperature based on the graph or the problem. For the next segment of the graph, we will again use Q equals mc delta T. In this case, the liquid is changing from 0 degrees Celsius to 100 degrees Celsius, so we use the entire segment. But in some problems, only a portion of the segment will be used. Again, just be sure to choose the correct initial and final temperatures indicated by the problem. Finally, last segment of the graph, we use again Q equals mc delta T to find the amount of heat added for a given change in temperature. In this case, the gas is increasing temperature from 100 degrees Celsius, the boiling point, to a higher temperature. At times, again, you will only use a small part of the segment, so be sure to choose the correct initial and final temperatures indicated by the problem. So what about the other segments of the graph? Let's take a look at the first horizontal segment of the graph. Heat is being added, but the temperature remains the same. This is because the substance is undergoing a change in phase from solid to liquid or liquid to solid, depending on which direction you're going on the graph. Again, there's no change in temperature, so mc delta T cannot be used heat. Instead, we will use the formula Q equals m times L sub F, where m is mass and L sub F is the latent heat of fusion, which can be found on page 392, and this latent heat of fusion indicates what kind of material is undergoing the phase change. The higher the latent heat of fusion, the more heat's required to change the phase. We denote a gain in heat as a positive Q, which in this case would be considered melting. But if heat is lost or released, it is denoted as a negative Q, which would mean the object or material is freezing, solidifying. For the second horizontal segment of the graph, heat is being added, but again, the temperature still remains the same. This is because the substance is undergoing a change in phase from liquid to gas, or gas to liquid. Again, there's no change in temperature, so mc delta T cannot be used. Instead, we'll use the formula Q equals m times L sub V, where m again is the mass, and L sub V is the latent heat of vaporization, which indicates what kind of material is undergoing the phase change. The higher the latent heat of fusion, the more heat is required to change the phase. The values for latent heat of vaporization for common materials are given on page 392 of your textbook. Now, we denote a gain in heat as a positive Q, and in this case would be considered vaporization. If heat is lost or released, it's denoted as a negative Q, which would mean condensing. Let's take a look at a problem which deals with phase changes. How much energy does a freezer have to remove from 0.5 kilograms of water at 20 degrees Celsius to make ice at negative 6 degrees Celsius? Pause the video for work on the solution. If we look at the graph, we're going from liquid water at 20 degrees Celsius to ice at negative 6 degrees Celsius. For the first segment of the graph, the water starts at 20 degrees Celsius and loses heat until the water reaches the freezing point at 0 degrees Celsius. Note, we're not using the entire segment from the boiling point to the freezing point. We're going from 20 to 0. So we must use mc delta T for the water, decreasing temperature from 20 degrees Celsius to 0 degrees Celsius. Because the temperature is decreasing, we will get a negative Q, which means heat is being lost. For the second segment of the graph, the water is undergoing a phase change, freezing, or from liquid to solid. We cannot use the mc delta T equation because there's no change in temperature, so we must use the Q equals m times L sub F, the latent heat of fusion. Again, we use the latent heat of fusion for melting or freezing, not the latent heat of vaporization. Also, because water is freezing, heat must be lost, so the m L sub F must be denoted as a negative value. It won't come out negative on its own. For the final segment of the graph, the ice is decreasing temperature from 0 degrees Celsius, the freezing point, to negative 6 degrees Celsius, so we again use mc delta T for the ice. This will turn out to give us a negative value for heat, because the temperature is decreasing. To find the total amount of heat, we must take the sum of all of these values for each section of the graph. Plugging into the equations, minding that you must call the heat for phase change negative, we get the following. And solving for the total heat, we get negative 214,660 joules. Again, negative because heat is being released. Let's take a look at another problem involving phase changes. A 3 kilogram block of iron was taken from a furnace where its temperature was 700 degrees Celsius and placed on a large block of ice at 0 degrees Celsius. The ice melted, and the final temperature of the system was 40 degrees Celsius. Assuming that all the heat given up by the iron was used to melt the ice and heat the water, how much ice was melted? Pause the video for time to work on the solution. To start out the problem, we have to set heat lost equal to heat gained. Heat is lost by one of the objects, which needs to be negated. So on the left side of the equation, we have negative mc delta T, and on the right side of the equation, the object, or the ice, is gaining heat to change the phase and to change the temperature. We plug in the values that we know. We see that the only unknown value is the mass. Do some simple algebra. We find the left side of the equation to just be a number, and the right side of the equation to be a number times m plus another number times m. Adding the two numbers together, times m, we see that we can solve for mass, which is 1.78 kilograms. Let's take a look at our final problem. A 70-gram bullet traveling at 250 meters per second penetrates a block of ice at 0 degrees Celsius and comes to rest within the ice. Assuming that the temperature of the bullet doesn't change appreciably, how much ice is melted as a result of the collision? Pause the video for time to work on the solution. To start out, the bullet has kinetic energy, which is equal to 1/2 mv squared. We can find how much kinetic energy the bullet has by taking the mass, multiplying it by the speed squared, and multiplying it by 1/2. And we see that the kinetic energy is equal to 2,187.5 joules. Well, all of the kinetic energy turns to heat because the bullet comes to a stop. So, because no heat is lost, or no energy is lost, then the kinetic energy is equal to the heat, which is 2,187.5 joules. Because the heat that's being put in is causing the phase to change, we use Q equals M times L sub F for latent heat of fusion. And the latent heat of fusion for water is 333,000 joules per kilogram. Solving for mass, we get the mass to be 0.007 kilograms.